Hi guys, welcome to Sigma Maths. This is the third video in a series of videos covering the exponentials and logarithms part of the A-level. In this video we're going to look at 6.3, 6.4 and 6.5 of the Edexcel specification, which as you can see covers logarithms, the laws of logs and solving equations with both exponentials and logs in them. Now let's start by thinking about the equation y equals a to the x. This is the general exponential equation that we met in an earlier video. Now it would make sense to think if we can write the equation y equals a to the x, then there must be a way that we can rearrange this equation to make x the subject. i.e., how do we write an equation that says what power of a gives us y? Well, let's think about a numerical example to try and make this make a bit more sense. Let's take 3 to the x equals 81. Now when we say to ourselves what is x, the question we are asking is what power of 3 gives 81. Now in this case the answer to that question is 4. That's because we know that 3 to the power of 4 is 81. But that question, what power of 3, that's what the logarithm is for. So this is the inverse function of an exponential, in the same way that subtraction is the inverse of addition and division is the inverse of multiplication. So the way we would write that then, so x equals log, and that covers the what power of 3, or sorry, the what power of part. The 3 goes down here and is known as the base number, and then it's of 81. Okay, so just mention that base number again. So here in a log we say log base 3 of 81, and that links back in with the exponential equation where this big number here is called the base. So we can go in between exponential equations and log equations using this idea of the base number, and here we just write x equals 4 because that is log base 3 of 81. Okay, we'll do a couple of examples, but before we do that we're just going to make a note or put up the general formula for this. So y equals a to the x can be switched over into the log form of log base a of y equals x. Remember, that's what power of a gives me y. That's what that's asking. What power of? Okay, now there are some common bases that are so commonly used that they have special notation, so we'll just make sure we're aware of what they look like. So common bases, we've got e, which we met in a previous video. That's the 2.71 something special number, a lot like pi. Refer back to the first video if you want to have a bit more explanation about that. If we're looking at inverting that natural base e to the x, then we use log base e. Now you won't really see this expression log base e anywhere because we have a very commonly used replacement for that, ln x, basically meaning natural log. That's why we've got the n there, of x. So that would be if you had something like y equals e to the x, that would turn into x equals ln y. So that's the converting between exponential form and log form of the same equation. And then you've also got base 10. Now base 10 is obviously very common because we work in a decimal system. We work in powers of 10. So if we had something like y equals 10 to the x, we would rewrite that using log. Now, so because base 10 is so common, you'll notice in textbooks and other various places that if the 10 is just dropped, if there is no base specified at the end of the log, then it will be log base 10. So this would be rewritten as x equals log y. Okay, so when you see log without a base, it's very likely that it means to be base 10, and if you see ln, then you know it to be log base e. Okay, let's just do a few examples over here to see this in action. So we could work out the value of log base 16 of 64, and we'll call that x. Okay, so let's have a look at this. What power of 16 gives us 64? Let's rewrite it in the exponential form just so we can get more used to this converting between the two. So we always look for our base number. That's the small number just next to the log. So that's going to be 16 Now this is what power, which means the thing on the other side of the equal sign is the power. 16 to the power of x equals the thing inside the log. What power of 16 gives us 64? Okay, so hopefully you're thinking, okay, there is no direct power of 16 that gives me 64. So what we're going to have to try and do is get these into a common base so that we can work with things like fractional powers to get there. So first of all, we're thinking of 64. How can we write that as a power of a smaller number? So we've got two options. We can either do it, well actually we've got more than that, but 8 squared might come to mind. However, 8 cannot be raised to a power to give 16. So let's try 4 cubed. That works quite nicely because 4 can be raised to a power, an integer power, to give 16. So if we write that 64 as 4 cubed, then we can write 4 as 16 to the half. Okay, raised to the power of 3. So that all equal to each other. 64 is 4 cubed. All I've done here from this step to the next step is replace the 4 with 16 to the half, because that's the square root of 16, which gives us 4. And then we've got the power of 3 still left there. Combine those powers together. Remember, power to a power rules is that we multiply. We get 16 to the power of 3 over 2. So comparing that back to the left hand side, we can see that x must be 3 over 2. Okay, so really you have to get to know your powers, be very good at moving in between powers, and good at your indice laws as well, and using your fractional powers and negative powers to basically work your way to the thing that you want. Now this is a nice example, an example that gives a rational answer. It is possible just to put this into a calculator, and sometimes you will have to work out logs that you can't do in your head, because it would be something like, I don't know, log base 2 of 3. Well, there is no easy power of 2 that gives us 3, so you would have to use your calculators to work out the log value for that. A simple log button, just type it in. Okay, now that we've had a good look at going between an exponential equation and a log equation, it would make sense now to have a look at the graph of log. Now, video 1 had a close look at the graph of the exponential functions. You'll remember that it was an increasing function. As x increased, y increased. It went up very steeply for positive x values, and then it went down to that asymptote for negative x values of x equals 0. Now, when we think about the graph of an inverse function, we know that we are basically flipping around the input and the output. And this will always be the same as a reflection in the line y equals x, because that effectively takes every single point on the curve and it swaps the coordinates around. Okay, xy becomes yx. So let's have a look at what that looks like. So we just label my, there we go, axes. So the red graph, this is y equals 10 to the x. I thought I'd go with that common base 10. And then the blue graph would be y equals log x. Remember, I don't need to put the base 10 because it's known that if there's no base written next to the log, then it is base 10. And then, as I mentioned, I just put the green graph on there so you can see that's the line y equals x. So on the exponential graph, we went through the point 0, 1. You can see this has been reflected in the line y equals x, and the log graph goes through 1, 0. Okay, so really it's quite easy to remember the log graph if you just start with picturing the exponential graph in your head, think about the key features, and then reflect all of that in the line y equals x. You can also see that the asymptote that was y equals 0 for the exponential graph is now x equals 0, so a vertical asymptote for the log graph. So just a nice reflection. Okay, well that's our introduction to logarithms. Now we are going to have a look at the laws of logs. Now we're going to start off by thinking about some fairly intuitive laws. So I just want you to consider log base a of a. Yeah. So remember what that's asking? It means what power of a gives me a? A to the 1. Okay, so that's just a kind of like I don't know, an identity case. And then we've also got log base a of 1. Now, if you've been paying close attention to the graph on the previous slide, then you already know what the answer to this is, but let's think about it in terms of what power of. So what power of a gives me 1? Okay, well that just brings in the anything to the power of 0 equals 1 law, so we get 0. Okay, so we've got these like standard set to all for all values of a, positive. Let's just bring that up. There we go. We've got log base a of 1 is 0 and log base a of a is 1. That can be helpful when you're trying to simplify things. Whenever you spot it, you want to use those, show that you know what you're talking about. Okay, now the rest of the laws tie in very tightly with the laws that you know from your indices. So let's just remind you, index laws. So what I mean here is when we do things like a number with a power multiplied by another number with a power with the same bases, we know that that would result in adding the powers. We know that when we divide, we subtract, and when we raise to a higher power, we multiply. Okay, if we can have all of these laws of exponentials, then we can have the equivalent laws, but as logarithms. So let's have these come up on the screen now. Oh, wrong one. There we are. So if we add logs, that's the same as multiplying what's inside. So that's the inverse of the first law. If we subtract logs, that's the same as dividing inside. That's the inverse of the second law. And then finally, if we multiply outside the log, that's the same as raising to a power inside the log, and that's the equivalent of the third law. So if you know your indices laws well, which you should do from GCSE, then it shouldn't take too much to translate those over into the logs. Okay, and there, just quick mention, because it's in the specification, there is this change of base formula here. Now this little bit down here I have grabbed straight from the Edexcel formula sheet, so you do not need to remember this law. You do need to learn all of the other ones, but this one down here, you do not need to learn it, but it is, you just need to be aware that it is there in the formula sheet if a question needs you to go from one base number to another base number. You also get this little snippet here, which doesn't overly help you, because if you've learned all your log laws and you understand what exponentials and logs are, then you'll know that is what it is anyway. Okay, so let's just do a couple of practice questions implementing these laws of logs. To be honest, you don't need to set aside time to sit and just really learn these. You just need to do a bunch of practice questions and you will get to know them very well. They should just become part of your maths toolbox that just kind of naturally sits there as long as you're continuing to keep up regular practice. Okay, so let's do some examples. How about evaluate a third log base 4 of 64 plus 2 log base 5 of 25. Okay, so using this log law here, multiplying outside the log is the same as raising to the power inside the log. That would give us, oh, sorry, no, I don't want that. Okay, that would give us log base 4 of 64 raised to the third. Okay, and now over here, now I could take the 2 in and do 25 squared, but that's a rather large number. So this part of the expression, I'm just going to say 2 times and then log base 5 of 25. What power of 5 gives me 25? 2. Okay, so we can just evaluate that one. We could have done that with the first part, but we wanted to have a go at using these new log laws, so we wanted to take the third inside. Now 64 to the third, that's the cube root of 64, is 4. So this becomes log base 4 of 4 plus 2 times 2 is 4. Log base 4 of 4, either straight away you know that that's 1 because you've got used to this rule up here, or you think, okay, log base 4, that means what power of 4 gives me 4? 1. 1 plus 4 equals 5. Okay, so if you want to see more practice of using the log laws, especially using the log laws to solve equations, then check out the video after this, the 4th video in the series. We'll be going through lots of practice questions in that one. Right now though, we're going to move on to looking at solving equations involving exponentials and logs. Okay, so we are going to start with a general form of an equation. So let's call it, just thinking, a to the bx plus c equals p. Okay, so if you're given an equation of where a, b, c and p are all numbers, and they're asking you to solve it for x, so I'm just going to leave these as letters just as like a general form of the equation. We'll have a go at practicing some examples of these in the next video. Now I want to show you two different ways of approaching the solving of an exponential equation, because there are two ways, and one way seems more intuitive because it uses the rewrite it as a log equation method, but then there are particular types of exponential equation where that's just not going to work. So let's just start with method 1, which is to rewrite this as a log equation. Okay, so we know our base number is a, so we start off with log base a of the thing that we're aiming for. So what power of a gives us p? That's the thought process. And that must be equal to the answer of what power of a gives us p, which in this case is just the bx plus c. Okay, so base number raised to this power equals this. And then, considering the fact that a, p, b, c are all numbers and we're trying to find x, this just requires a rearrangement. So at the moment, x is multiplied by b and we're adding c. So we're going to subtract c, so log base a of p, which will just be a number, minus c, and then divide by the b. And we have x. We will have solved. That will probably go in our calculators, or the question may be asking for an exact answer. We'll be very careful, make sure we read the question, in which case we will probably leave it in exactly the form that I've given it there, but with a bunch of numbers instead of letters. Okay, the other way of solving these is to apply some form of log to both sides of the equation. Now, I personally like using the ln. It's good to become familiar with ln, and also in terms of using it on your calculator, it depends what calculator you've got, but my one, which is the Casio Class Whiz, it doesn't have a log base 10 button, but it does have an ln button. Now, I can put in log base 10, but I would have to press the log button and then input base 10, whereas I can just press the ln button and I don't have to press any extra buttons. So personally, I like to use ln. You could use log, as in log base 10 if you preferred, but the idea is that you basically apply your chosen log function. It doesn't have to be the same base as the one in the equation, so I'm not using log base a here, I'm using log base e. You apply that to both sides of your equation, and what that allows you to then do is implement one of your log laws, which is where you bring the power down. So here you can bring down the bx plus c now multiplies in front of the ln a. I'm just going to drop the brackets there for ln p, so I don't need to have them. And then ln a and ln p are just numbers. I'm not going to put them in my calculator yet because they're going to be most likely irrational numbers. So absolutely fine to leave them as like ln 2, ln 5, whatever the numbers happen to be. But now we just need to get x to be the subject. So we're going to multiply this out. Now I suggest that you always leave your lns at the end of your terms. So I'm not putting b ln a x. That's because I don't want people to, or even myself if I'm not thinking straight, to think that that means ax inside the log. I need to make it clear that the only thing that's inside the log here is the a, so that's why I always put my lns at the end of the term, whereas normally you're used to putting your variables at the end, so your x's, but special case here, take our lns at the end. And then from here we can just see that we need to subtract c ln a and divide by b ln a, because that's what's multiplying the x right now. So we would have ln p, we would minus the c ln a, and we would divide that all by b ln a. And again, if these were all numbers, we would check the question and make sure that we didn't need to give our answer in exact form. Otherwise, we would grab the calculator and pop that in. Okay, I want to have a look at the general form of a log equation now. So I'm going to write another one over here, log base a of bx plus c equals q. Okay, so general form of a log equation. That could be ln, it could be log, it could be whatever you want. Now this time the best way forward is to go and convert it into the opposite type of equation, so that's convert it into the exponential form. So we're going to take our base number a, raise it to the power of what's on the other side, q, and then that will equal what's inside the log, bx plus c. Okay, so now this is just a number, a to the q is just a number, b is a number, c is a number, so I can just rearrange to make x the subject. So we are going to have a to the q minus the c all divided by b. And we're done. Now, I do want to just quickly mention, in case you're thinking, well, you went on about these two different methods for the exponential equation solving, and you said that for a particular type of exponential equation we'd have to use method 2. I'm just going to show you what that looks like now. So if I give the example of 7 to the power of y plus 2, and then, so this type of equation is one where we have two different base numbers, okay? 9 to the y plus 1. So the reason I'm saying we'd have to use method 2 here is because if I try and do log base 7 on both sides, it will deal with this side, but it will not deal with the base number of 9 on the other side. I cannot deal with both bases at the same time. So this is when I do have to implement that applying a log to both sides. So we're just applying it. It doesn't cancel out with either of the base numbers because the ln is a different base to the 7 and the 9. But like we saw in an example a moment ago, we can bring our powers down. So y plus 2 gets brought down in front of ln 7. Y plus 1 gets brought down in front of ln 9. And then we can expand. So y ln 7 plus 2 ln 7 equals, oh, it shouldn't be an equal sign there, y ln 9 plus 1 lots of ln 9. Okay, now we just need to get our y terms on the same side. So y ln 7, and then we'll do minus y ln 9. And then we'll take all of our non-y terms to the other side. So ln 9 minus 2 ln 7. Okay, we're going to factorize because we're not going to evaluate our logs yet, our lns, our natural logs, because we're likely going to need to give this answer in its exact form. Plus it's nicer to do it that way. No need to touch a calculator in that case. And then we just divide by what we factorized out. So ln 9 minus 2 ln 7 all over ln 7 minus ln 9. And there we go. We are done. Okay, so there are other types of equations that you might come across. For example, you can have a mixture of exponential and quadratic. You can have simultaneous equations. Log equations that use all of your log laws combined in order to get to an answer. We're not going to go through that in this video though. This was just a case of basically learning the content. In the next video, however, we are going to go through a lot of practice questions on all different types of equations, which I will actually show you now so that you can have a go at these questions before you have a look at the next video. So we've got questions 1 to 8 on the screen now. So maybe pause, have a go at all of these yourself. Remember, you don't really need to use your calculator for most of them. Some of the solving questions might require to use your calculator if you were going to give your answer as a decimal. And then also we have a few more questions, so let's get rid of those. Questions 9 to 14 on the screen now. Again, pause the video, have a go at them, and then if you look for the 4th video in the series, so it's the video after this, with the same name, with the word practice on the end, then I will be going through all of these questions and you can see how you've done. Thank you for watching. If you found it helpful, please don't forget to hit the thumbs up button and subscribe if you want to see more videos like this. See you in the next one. Bye.